So as we mentioned before, most of the data, especially in engineering and physics or science, is actually not linear. And I've already shown you that there's a way to solve this, and that is one, to transform the data into a linear model. But if this can't be done, then we could use something called polynomial regression. So our least squares method from the previous sections can be extended to any higher order polynomial. So let's say if we were looking at a second order polynomial, y equals a0 plus a1x plus a2 x squared plus our error term. Now, as in the case with the linear, the linear least squares, the sum of squares of the residuals, SR, can be written as sum from I equals 1 to n of yi minus a0 minus a1xi minus a2xi squared, and the whole thing squared. So if we use the procedure from the previous method, we can calculate the derivatives of the sum of squares of the residual with respect to each coefficient. That is, the derivative of SR with respect to A0, SR with respect to A1, and SR with respect to A2. So if we do this for each case, we'll have an idea of how the sum of squares of residuals varies with each of these coefficients. And if we wanted to find the minimum value, we set these all equal to 0. And if we rearrange that equation, we get the following. That is n a0 plus sum of xi multiplied by a1 plus the sum of xi squared multiplied by a2 equals sum of y. We also have the sum of x multiplied by a0 plus the sum of xi squared multiplied by a1 plus the sum of xi cubed multiplied by a2 equals the sum xi yi. And lastly, we have the sum of xi squared a0 plus sum xi cubed a1 plus sum xi to the power 4 multiplied by a2, and that's equal to the sum of xi squared y of I. So now we have a set of linear equations, and we can solve these to come up with a solution for a0, a1, and a2. And this technique can be extended to any nth order polynomial, and we would have to solve a system of m plus 1 linear equations. So remember, we just now we're looking at a second order polynomial, and we have three simultaneous linear equations. And for the nth order polynomial, the standard error, s y over x, is equal to sum of the square of the residuals divided by n minus m plus 1 square root, because we are losing m plus 1 degrees of freedom. So let's have a look at this with a problem.